If you want to fill them with air, bomb them. If you want to fill them with water, torpedo them. The standard question of every torpedo pilot has always been, when do we get a torpedo that can be launched from high altitudes and great speed? The answer is that we have such a torpedo now. And here it is, launched at 260 knots and 800 feet. What's more, it's running hot, straight, and normal. All torpedoes of the Mark 13 Mod 6, 7, 8, and 9 type look pretty much like the older models. So what has revolutionized the performance of the torpedo? The shroud ring, commonly called the ringtail, Mark 1 Model 0, in conjunction with a drag ring on the nose of the torpedo, does the trick. This is a steel ring welded to guide vanes of the new torpedo. Using this ringtail with a nose drag ring and wooden stabilizer, successful test drops have been made at 2,000 feet with a speed of 350 knots. Optimum performance is obtained at about 800 feet and 260 knots. The stabilizer is secured to the ringtail with wooden dowels which shear on contact with the water. The drag ring has two primary functions: to aid in air stabilization and to decrease the impact shock about 40% on hitting the water. This is especially useful in cases of extremely high altitude drops. In a torpedo drop, any deviation from true air trajectory is liable to cause damage on impact. The drag ring helps to eliminate pitch and yaw. Like the stabilizer, this disintegrates when it hits the water. A valve, the water trip delay valve, prevents the torpedo turbines from burning up during its long air travel. On leaving the plane, the torpedo is operating only by compressed air. Impact with the water trips the valve, starting normal fuel operation. This valve is secured with wire to prevent the airstream from springing it. Similarly, high speed and altitude make it necessary to prevent the impeller on the exploder mechanism from turning while in flight. A piece of .020 annealed soft copper wire is used. Impact with the water will shear the wire. At high altitudes and in cold climates, special precaution must be taken to ensure a sufficient amount of antifreeze in the water chamber of the torpedo. Buoyed instructions should be followed. With the new Ordals enforced, not only will the torpedo be more stable in the air and in the water, with no appreciable broaching or hooking, but initial dives in 85% of cases will be no deeper than 50 feet if the proper entrance angle is used. Remember that proper depth settings must be determined for the type of target to be attacked. This should be in accordance with tactical doctrine. Depth settings as shallow as 5 feet may be used successfully. Against armored vessels, it is necessary to set the depths to strike below the armor to achieve maximum destruction. However, take care that the torpedo is not set so deep that it will pass under the target. Recent statistics show that of 2,000 torpedoes dropped under varying conditions, about 92% ran hot, straight, and normal. And in combat, the percentage of hits with torpedoes is greater than that of any other form of attack against shipping. And experts have figured that the plane is now from 40 to 50% less vulnerable to enemy anti-aircraft fire when using the new recommended high-speed, high-altitude approaches. Torpedoes were formerly dropped at low altitudes and low air speeds, so air travel was nearly negligible. However, using increased speed and altitude combinations naturally increases air travel. The old axiom of releasing at 1,000 yards does not hold water. In many cases, the air travel alone is 1,000 yards or more. At present, the torpedo is set to arm with a run of at least 260 yards. However, an additional 140 yards is added in alt sighting tables to compensate for possible torpedo and pilot error. So no matter what speed-altitude combinations are used, the torpedo should hit the water about 400 yards from the estimated point of contact with its target. A chart to serve as a torpedo launching guide has been published in Naval Aviation Confidential Bulletin for July 1944. A combination of any two coordinates gives the other three. For example, enter the chart with a dropping speed of 260 knots and a dropping altitude of 800 feet. This will result in an entrance angle of about 28 degrees, a time of fall of 7 seconds, and a horizontal distance of 3,000 feet between points of release and water entry. 3,000 feet is 1,000 yards, to which 400-yard water run must be added, giving a total horizontal range of 1,400 yards, from point of release to point of hitting target. When a torpedo is dropped, the crosswind acting on the plane at release imparts a motion to the torpedo, which acts on it throughout its time of flight and is in addition to the motion of the plane. The same chart can also be used for determining the amount of crosswind effect on a torpedo drop. So at 800 feet, the torpedo takes about 7 seconds to fall. A simple formula works out the rest of the problem. Crosswind effect is equal to the time of flight of the torpedo in the air in seconds times the velocity of the wind in feet per second. In making allowances for crosswind, the only effect to be considered is that on deflection. The effect on range may be disregarded. Always apply wind allowance on the side from which the wind is blowing. Disregard winds with relative bearings of less than 30 degrees or more than 150 degrees. Winds on the bow or on the quarter have only a slight effect on deflection, but winds on the beam may require important corrections which must be made. The following tables present practical aiming allowances. Mount these tables on cards where they will be easily available to the pilot. For winds of varying velocities on the bow or quarter, for two different sizes of ships, these allowances in ship lengths should be made. For winds on the beam, note the great allowances in ship lengths which must be made. Get these tables from your instructor and study them. Tables for aircraft torpedo sighting and launching data have been prepared by Buord and published as training literature by CNO. Let's break down Table 4 and see how it works. Altitude of 800 feet, estimated target speed 20 knots, and its length about 600 feet. Aiming point is 1.15 ship length ahead of the bow. Your own ground speed is 260 knots. Slant distance to point of impact should be 1,457 yards. Entrance angle of the torpedo will be 27 degrees and 20 minutes. You are approaching with a target angle of 60 degrees. So your radar slant range from the target at point of release should be 1,590 yards. Problems with other factors can be worked out in similar fashion. This chart should include data for shallow water drops, using these combinations of airspeed and altitude of release. Here, speed in knots is roughly equivalent to altitude in feet. Radar slant ranges are roughly 700 yards less than those recommended for open sea drops. The toughest part of the new aiming problem is releasing the torpedo at the proper range. Primary dependence must be placed on radar ranging until the pilot becomes proficient in visual ranging. A tactical use of radar for torpedo dropping can be to locate the target and commence the approach above the clouds. Then dive through the clouds to make a visual attack. Another possible use is attacking anchored ships, using radar for ranging as well as locating, with a drop through the low overcast. A torpedo pilot may in general drop and hit within a wide band of ranges. But if the range is too long, the torpedo water run will be longer than desired, and the average torpedo speed will be consequently slower, so that the torpedo may pass astern of the target or allow the target sufficient time to maneuver away from the torpedo. Likewise, dropping at excessively short range is just as bad, since the torpedo will hit the water too close to the target and so cannot be properly armed before hitting the target, if it hits at all. To emphasize the importance of ranging, look at what happened in one combat mission. The returning pilots reported that they had dropped at ranges of between 1,000 and 1,600 yards, and at altitudes of from 275 to 300 feet. But actual photographs proved that the ranges averaged 2,800 yards and the altitudes 190 feet. What a waste. And naturally, there were no hits. Remember that ranges are usually underestimated, so plan to counteract this tendency. Dropping altitude determination is of course assisted by instrumental aids such as the barometric and radar altimeters. However, neither of these is totally dependable under varying conditions of atmospheric pressure, technical limitations, and aircraft speed, altitude, or angle of glide. The seaman's eye method developed by training often must be used, although with a new torpedo, altitude control is not too critical except in shallow water drops. The full range of entrance angles is 18 to 22 degrees for shallow water, 22 to 32 degrees for open sea or deep water. Naturally, the extreme should be avoided if possible. If an entrance angle under 18 degrees is obtained, say 12 degrees, the result of a speed-altitude combination of 200 knots and 80 feet altitude, the torpedo may be seriously damaged and ricochet or broach violently. If the controls are damaged, as they probably will be, the torpedo may sink, or at least have an unsatisfactory run. If the entrance angle is steeper than 32 degrees, the usual result of dropping from high altitude at low speed or dropping in a glide of over 10 degrees, not only is there the danger of the torpedo hitting bottom because of the initial deep dive, but the torpedo may stub its toe, which may cause structural damage or damage the steering mechanism, causing premature sinking or a very erratic run. Target angles are between 0 degrees and 90 degrees, since attacks from abaft the beam should be avoided whenever possible, because a fast-moving target can run away from the torpedo or maneuver to comb the torpedo tracks. In any case, small errors in range estimation on stern shots will cause misses that might have been hits with the same error on bow shots. Also, stern approaches will expose pilots to AA fire for a longer time, as closer drops must be made. Obviously, it is best to drop at an angle where the longest target is offered to the torpedo at impact. Perfect conditions would be a drop in which the torpedo ran at an angle of 90 degrees to the path of the ship at contact, or as close to that as practicable. If you want to hit them, you have to lead them, the right amount. The range to the aiming point is dependent upon the air and water travel of the torpedo. The range to the target varies with the target angle and speed and the range to the aiming point. By previous training, the pilot should be able to estimate automatically his own altitude and speed. Aiming problems are now comparatively simple. Observe the target length, speed, and course, and from this, select the aiming point. Then estimate the range to the aiming point. The target angle controls the range to the target, and this can be used to assist the ranging to the aiming point. Keep a rough check on the target angle, using radar and seaman's eye to check the slant range to the target. The actual ship lengths to be allowed for are measured from the bow of the target vessel along the course line extended to the aiming point, which is the center of the ship at the intended point of contact. Assuming an underwater run of 400 yards with a proven new torpedo speed of 32 knots, here is a thumb rule that can be applied against a 600-foot target on a steady course, wind force 0. For 20 knot speed, aim 1 ship length ahead. For 25 knot speed, aim 1.5 ship lengths ahead. For 30 knot speed, aim 2 ship lengths ahead. For a 400-foot target vessel under similar conditions, the aiming allowance is 1 ship length more than for the 600-foot target. It figures out that 1 ship length should be allowed for each 10 knots of target speed from 20 to 30 knots. So for 20 knot speed, aim 2 ship lengths ahead. For 25 knot speed, 2.5 ship lengths. For 30 knot speed, 3 ship lengths. Study enemy ship characteristics and data on bow waves and wakes to determine speed. Under torpedo attack, it can be assumed that ships will use full power in attempting to maintain top speed. However, remember that any ship will gradually lose speed in a sustained turn. This loss is important and must be considered. Circling ships will have a deceptive weight due to the churning of the propellers and the position of the rudder. When selecting aiming points for maneuvering targets, 3 additional factors are involved: the direction of the turn, the degree or rate of turn, and the decrease of speed of the target in the turn. In this example, assume that the target is in a developed turn and is using full power and full rudder of 35 degrees. The aiming point depends upon the ship's actual speed in the turn and must be measured from the bow along the ship's curved path extended. The curved wake indicates this path. In general, large ships capable of 30 knots at full power and continuing to use full power in the turn will decrease speed by about 12 knots after a 90-degree change of heading. The ship will then be able to maintain about 18 knots as long as it continues in this turn. The destroyer class of vessel loses only about 5 knots of speed in a similar turn. To estimate the aiming point for targets in a developed turn, use the actual speed the target has. That is, taking into consideration the loss of speed in the turn, and measure this along the curved path of the ship, using the thumb rule measurements of a non-maneuvering target. If the target is just commencing its turn, the loss in speed will be only about half of that lost in a developed turn. In this type of turn, an undeveloped turn, in general, the aiming point is almost identical with that used if the target is on a straight course. For attacks on a turning target, the best target angles are on the outer bow from 0 to 60 degrees. On the inner beam, the best target angles are between 90 and 150 degrees. In any case, the actual target size presented to the torpedo is the controlling factor. For a U.S. Navy light cruiser using full rudder of 35 degrees and 30 knots initial speed, it takes the rudder about 23 seconds to become fully applied, and about 10 more seconds for important changes in the ship's heading and position to take place. The use of high speed and correspondingly high altitudes naturally calls for entirely new tactics, and therefore a new concept of training. so that the pilot is equipped with the knowledge and experience to put these new tactics to use. Training for torpedo dropping should follow a fairly definite pattern. First of all, study and talks with experienced pilots and crewmen. All available Buord publications and official dispatches should be considered carefully. The pilot should then commence training with dummy runs. After making proper dummy runs checked with the F-46 camera, he should then use concrete blocks or dummy torpedoes. This can be followed by live torpedo drops, all with single planes. As many torpedoes as possible should be dropped. Statistics indicate that for best efficiency, the average pilot requires at least 6 single live drops before graduating to group work. Strengthened exercise heads, as provided by Buord, should be used. Sections of 3 or 4 planes should then work together, followed by practice with divisions, then with squadron attack, winding up with coordinated attacks with fighters and dive bombers. In each case, whether single planes, sections, divisions, or squadrons are used, dummy runs should be made in sufficient number to ensure best results for the final live runs. During all of this, trained pilots should be used as observers and consulted after each run. It is helpful to think of the attack in 3 phases: the approach dive, the attacking dive, and the aiming run, then retirement. In addition, pilots dropping torpedoes should record pertinent data for comparison with photographic data. Another very important factor in training as well as in combat is the correct use of photo assessment. The study of photographs from the F-46 camera mounted in TBMs will prove an incentive to good pilots and show up bad pilots. In combat, the photographs will also serve as a final means of recognition and verification of results. It is essential for proper training to furnish the pilot with high-speed maneuvering targets for torpedo dropping practice. These targets should not be smaller than a DD. The new technique of torpedo dropping makes it almost imperative that the final torpedo attack be initiated in a glide of 20 to 40 degrees from no less than 5,000 feet altitude. The range will then be about 3,500 yards. As the plane approaches the correct dropping range for the speed and altitude combination selected, it is pulled up to level flight momentarily and the torpedo released. Drop should be from level flight, although it is permissible to drop in a glide of not more than 10 degrees. But note that this will affect the air travel. However, good performance does require that the wings be level and that the plane not be in a slip or skid at the moment of release. For an example of good technique, suppose the final glide is commenced from an altitude of 7,000 feet and 8,000 yards radar slant range. The pilot selects a point about 1,500 yards short of the target and commences his approach as if he were going to glide bomb the point selected. The resultant glide path will be roughly 30 degrees during the glide. Speed approaches 300 knots. Target maneuvers are offset by changing direction of glide as necessary. Flying to the release point selected, the pilot maneuvers the plane without wasting any time so that its flight, course, and his aiming are exactly correct when the release point is reached. The pilot decides he will release at about 800 feet. Around 2,000 feet and 2,500 yard radar slant range, he commences a smooth pullout. The plane should be leveled off and ready to release the torpedo about 800 feet altitude and 260 knots, with a radar slant range of 1,500 yards. As a general rule, pilots commence attack too far distant from the target, resulting in a final low, slow approach. Planes other than torpedo planes will adjust these tactics to their own individual performance possibilities. An SB-2C with dive flaps can make a steeper dive, leveling out just before dropping. Tactical advantage and surprise can be affected by utilizing approaches almost the same as dive or steep glide bombing. This type of attack has interesting possibilities and should be exploited fully. When the torpedo has an external installation, this nose cap reduces much of the speed lost due to wind resistance, thus increasing combat range. This is accomplished at small sacrifice in air stabilization and small cost in damping out initial shock. All torpedo attacks must be coordinated with attacks on the major targets and screening vessels, using one or all of the following: dive bombing, strafing, or rocket attack. Unsupported torpedo planes should never attack well-defended ships. High-speed and high-altitude approaches by torpedo planes require much less time to complete than the method formerly used of losing altitude well away from the target and coming in low. This requires that commencement of the torpedo attack be withheld until bombs are actually dropping. If torpedo attack is supported only by strafing or rocketing, both attacks should start simultaneously. The VF attack is pressed in quicker, and if they hesitate at all, they will be too late. This is not only for diversion, but some anti-aircraft guns may be put out of commission, and possibly the torpedo planes will be offered a target whose speed and maneuverability has been greatly reduced. Timely and determined fire by all guns of a torpedo plane will appreciably reduce and has on occasion stopped AA fire from vessels within machine gun range. Concerted attacks by supporting VF will also assist torpedo planes in retirement. The torpedo is still the most potent single weapon of destruction against enemy shipping, but only if used properly. It's up to the pilot to see that it is used properly, making the most use of these recent improvements. This will be the result.